welcome back to our discussion. So if you remember, we are treating module 5, right? And module 5 is all about what? Instance-based learning. Instance-based learning, right? So in instance-based learning, we are able to look into your neural network. I mean, not neural network, your k-nearest neighbor. And we also looked into what? Your locally weighted regression. Now, for us to proceed, we need to look into what we call what? The RBF, which stands for Radial Basics Function. So, in today's class, what we'll investigate is your what? Radial Basics Function. So, whenever you hear RBF, so we use it RBF for short. Okay, and we look at some motivations behind this, motivations, and then we look at, can I say, some mathematical relationship, but prior to that, we see the algorithm, okay, and then we try to compare your RBF versus your what? ANN, right? We take a kind of an illustrative example, and then maybe we summarize by looking at some salient features. Summary, okay? Now, one thing we know for sure is that whenever we talk about RBF, we are actually talking about what? We are talking about what exactly, guys? We are talking about an approach or a function, right, that closely mirrors that of your distance weighted regression and your artificial neural networks. Fine. So when you hear of the keyword, or when you hear of the term RBF or Radial Basics Function, we are actually telling you it's a kind of an approach to function approximations that is closely related to your distance weighted regression and also to your ANN. Fine. So in this approach, we need to come up with a learned hypothesis that is a function of a term, say f of x, such that it takes an initial weight as input, try to sum that over some weighted distances by using some kernel functions based on sets of instances which we give. So if you permit me to model this, we will talk about this RBF is a kind of an approximation function function. So we call it what now? F of x hat, such that f of x, that function approximation, will be equal to some initial weight, right? Which we sum up over some sets of intervals, right? Provided that that x belongs to the what? The class, right? Now, we are not talking about this distribution, okay? We will now say that what? The value which we are going to compute, which is what? Your weighted distance, does not belong to this distribution. Rather, the value goes from what? 1 to k. And in this case, what we have is what? You guessed it. We will have an initial weight, we call it weight vector of that, right? Multiplied by the kernel function. Yes, that kernel function which computes the distance over the sets of instance, say xu, comma x, right? Provided that u goes from 1 to k. So we need to define some terms here. So before we define any term here, let's call this equation 1, and that makes sense now. Now, for us to define this now, we will now say, what are these terms now? Can we give it a name? Yes. So where we define most of the terms now, where x of what? U is what? Is an instance from what? Or is a subset of the sets of instances. So if I say that x of u, this, I'm talking about this, is a subset of the sets of instances, right? That means that this belongs to this, yes? and that the kernel function, and that this and this, what is it we are talking about? Ku of the distance between xu, comma, the instance is equal to what? The kernel function. So, and usually we tell this kernel function is kind of a numerical value. It takes a kind of a constant value, right? So, and we know that this kernel function will decrease as the distance increases. So, this is the kernel function such that this kernel function, such that the kernel function, okay, I'll continue here, such that the kernel function Ku of what? Of xu, comma, x decreases as the distance increases, right? As the distance increases. Yes? So, and now you know the concept of variance, right? Like to kind of predict the variability of a given instance. So we center this, and I say note that this now, note that f of x will be what? Centered. F of x will be centered close to the instance xu, right? And some variance, So there will be some variability and some variance, right? Yes, at that point. So this makes sense now. So when this holds true, we can now rewrite this approximation function to look like this. How will it look like? So we rewrite this. We rewrite as now Ku of what? Of that, right? X, Q, comma, X to be equal to, now we take an exponentiation similar to your log function of what? The variance, such that we'll be able to minimize the distance or the squared error. Okay, in this case, let's not confuse two things. So that we'll be able to minimize the distance between them. Hence, this will look like this. 1 upon exponentiation of what? What is that? What? 2 the variance whole squared. Variance is variance of u at that point. So we are talking of the point u, right? So we have this, okay? And multiplying to the distance squared of what? Xu, comma, x. So this approximation function will be rewritten as this, right? So now this tells us that the functional form of this equation. So after this is rewritten, okay, so we can call this the conventional equation. So I'm just giving the name, the conventional, and this is the what? The functional form. Okay, so this is equation 2, this is the functional form, and the equation 1 is your conventional form. So this functional form of this equation can approximate any what? Function with arbitrary small error. And that's what we're actually talking about here, because if you remember the m of our what? The m of the function is to get to a global minima, right? So whereby the error decreases exponentially. So when the error becomes small, then we can actually know that definitely the model is fit for prediction. So that's what we said here, okay? That's what we're actually trying to reinforce. That this functional form of the what? Conventional equation, or equation 1, cannot approximate any function with arbitrarily small error. But that will not happen unless you have sufficiently large number of what? Kernels, okay? Of such Gaussian function, okay? And that the width of the variance can be specified separately. And because of this, the conventional form, or the equation 1, can be viewed as describing two-layered network. Now, when we talk of two-layered network here, just think of your what? Neural network. Two-layered network, where the first layer computes what? The values of the various kernel distances or distributions, and that the second layer computes a linear combination of these layers from the what? First unit layer. Now, what I have said is, in this case, when you visualize this as a two-layered network, now you can think of something like this. Think that you have some sets of inputs, right? So this is a basic neural network with some hidden layer in between, and then you have an output, say two outputs, say I'm talking about classification 1 or 0. Is it a cat or a dog? Cat or versus dog, right? So if this holds true, that means that at the first layer, this is layer 1, right? So that means there's another layer in between here before I get to my what? Output layer. So this is my layer 2, and then this is my output layer, right? So in the first layer, what I'm actually doing is, I'm actually looking at what? The weights, right? That contributes to the what? The value at this node. So that means if I check here, I think that now if it is fully connected, I will have weights coming from each node, from the input node to the respective hidden nodes, right? So here I have 6 weights here, from here to there, and then from here, that means that the output of this, let's say I have 2 nodes here in the second layer. Now this output of this will be primarily influenced by the input of the previous node. Then I have something like this. I'll make it fully connected again. Okay? Okay, something like that, right? And then this and that, okay? Now, and from here, this tends to this, that, and those. Fine. Then we get an output. Remember this output now, like, we call it O1 and O2, where here I call input I1 and I2. And after I get the output O1 and O2, I need to calculate the error, right? E1 and E2. Such that I'm going to sum these errors, right? And see if the errors are actually minimal, right? This is what we do, right? F this of that and that predicted. And then I minimize this and provided that this goes from 1 to this, right? So this is actually what we do when we compute the error. So this makes sense now when we get back to that definition and say that this function given by the conventional equation in equation 1 can be viewed as describing a 2-layered network where the first layer of the units are the values of the various kernel distributions, and where the second layer does what? Computes the linear combination of these first unit values. So with this, we will look into an example of an RBF network and how this RBF network closely mirrors your neural network. Now, what exactly are we talking about here? So the first stage is like you choose the number of hidden layers. Can we call it that? So stage 1. So there's a 2-stage process involved. The 2-stage processes are the 2-stage processes involved include, so the first stage, the stage 1. So we choose K, okay, over some units, okay, closer to some instance, some paraphrasing to some instance, such that the kernel distribution of this over the distance of what? X, U, comma, X holds. And stage 2 says what? In stage 2, it says that we need to do what now? Assign weights so that we will maximize the training. So when we hear of the fit method, or what in Python, what we are actually saying is when we train this network, has it actually learned? And that learned only when we have done the weight update rule through a method we call what? Gradient descent. So you see here, in this case, now the weight of the training network is selected in such a way that it maximizes the what? The training data, right? By making sure it gets to the what? Global convergence. So second step says assign weights. And we know they are called WIs or WU, okay? Such that it's what? Maximizes the objective function. So what's the objective function here? The objective function is to ensure that, which implies we need to minimize this error. Minimize the error. That is our core objective, error. Okay? The error, which is something as saying that compute the error such that this error is the difference between the what actual value and the what predicted value, right? And we always square this to make sure we remove what negative errors, because as you know, error can never be negative, right? And then we sum this up over some sets of instances, and this instance says that the instance must belong to the distribution, right? And that this error will always be halved. Okay, it's like you trying to minimize this error. And because of these kernel functions are held at the fixed stage during the second training, the linear weight can be trained effectively. Now the question is, how is it fixed, right? Because if you get back to your neural network, you see that when you do the weight update through, you are actually updating the weight closer to the hidden layer, and again you update the weight again backwards even closer to your input layer. But in this case, we said here, we are telling you that now that the error is fixed at the second stage. That means this error would only be propagated from your output only to your hidden layer and not to your input layer. And with this, we will now see how an LBF architecture or LBF network is different from your what? Your neural network. So whenever we talk about neural network, we always think of some sets of inputs with some hidden layers and some outputs, such that anyway I use only one hidden layer here. So this is layer 1. So that in this layer, I'm going to have H1, H2, H3, 3 hidden layers. I'm going to have out1, out2. I'm going to have I1, I2. And one thing that stands out is that the inputs to the hidden layer will be affected by what? The weights, which is usually initialized what? Randomly. And the weight is good that the weight always be made minimal. It's made small. So I have some random values, W3 through W6, and these values will be very small, right? Now, the question is, why must it be made small? Because in most cases, we don't want to overfit the model. We want to ensure that the patterns are being learned. Because if you fix this with a constant or an integer value, then it might mug up the pattern and it will not be able to adjust accordingly. So with this, I'm not talking about the activation functions now. That is out of question. Now, looking at this now, what we have is from hidden layer now to the output layer, again you have some. Now, these are actually edges, okay, of the neurons. So, but let's talk about the weights now. So another one, some weight vector will be there. Again, some weighted value, please. Again here, definitely we can represent all of them in a vector form, no problem, right? And outside this, there is also a constant value, right, which influences this. So that constant value is called the bias. So we have B1, and again there we have B2. And usually the value, I don't know why the value is always 1. So the reason is we wanted to start with a small value. The bias value can also be 10. It can also be, so it's kind of a hyperparameter again, which is always fixed before you start training the network. Now, this is what we have in your ANN. And what is the similarity between this and your RBF? So we have W7, which tends to again W12. So what you notice is this input, right? This output is highly influenced by this. So let's do a forward propagation. So this with this input moves to this hidden layer, goes with this input again, goes to the output layer. Now, if I do back propagation, what I'm actually saying is from the output, and that leads us to, at the output, we always calculate the error, E1, and then we E2, right? And then we find the total sum of error, so which called E total, which is what now? E1 plus E2. That makes sense in this case. So what we do when we do back propagation is we take this error, right? Error will be dependent on this. So error is dependent on this guy, right? Which is auto1. Auto1 will be dependent on this weight, right? We have that. And this way will be dependent on this, right? And this will be dependent on that, and then we go, right? But in an RBF model, what we'll have is, let's keep it like a tree, in which this is our objective function. Yes, we want to get to this, okay? F of x, yes? So this is the function. And in this f of x, there will be some nodes, some edges that comes to this way, that tends to this node. And in this edge, there is a kind of a function. Let's keep some notation there, right? And then this moves till there. Now we can actually call these some names, but let's get to that. Now in this case also we have some inputs, okay, that actually influences this. So I will tell you why I left this like this, okay? Now in this case we have some input values, right? Such that this is again is fully connected, so this node tends to that, this goes to that, so this is here, this also is there, and this is also there, and this goes to this, and this goes to that, right? So in a neural network, what happens is, if we look at this as inputs, and this is hidden, the hidden layer, you know what I'm talking about. When I talk of input, I'm talking about input layer, and then hidden layer, and then the output, which is the output layer, right? So here it is only one node, so it's good if I call it an output node. Now, did you see that when I do an await update rule using back propagation, I'm actually also going back, tracing this back to my initial input by updating the weights. But here, we are going to have weights, okay? So we will have weights now. We now do what now? If you remember, we have what? Some weights, W1, W2, W3, whatever. But in this case now, I've taken a bias of 1, so that the weight here becomes W0, and I'll tell you why. And then we have W1 and W2 down to what? Wn. Now the question is, why W not there? Why not W1? And why is it not taking an input, right? So this is the concept of my bias. It's a loose analogy of my bias. Did you notice something that whenever you want to compute this, what we do is, this is B, right? The value of this B1 is what? Is what? 1. So we now say that when we train this with forward pass, or call this forward propagation, says what? Take the inputs, W1, into weights, okay? Input into weights. Then you add bias, right? No doubt. And then with some activation function, right? Okay? And then you push it forward to the next what? Layer. So that makes sense now, because if you look at this, if the bias value is 1, this is similar to what now? W1 plus X1 plus what? W0. That's why you see here W0 plus W1 X1, okay, plus W2 X2 plus W3 X3, okay, W2 X2 down to Wn Xn, right? So this is also right. So this is what we now see. Now you can actually see the difference between your RBF, that is your Radial basics function, and your what? Neural network. So several alternate methods has been proposed in the literature for choosing an approximate number of hidden units. If you remember vividly, we are actually saying that there is no hard and fast rule of choosing the number of hidden units in a neural network. That all these approaches are still what? Experimental. So what we are telling you in that essence is, whenever we talk of this, we need to actually understand that there is no fixed rule or no fixed approach for doing this, for choosing the number of hidden layers. However, one approach is to allocate a Gaussian what? Kernel function for each of the training example, which is centered around the point. That means which point? The instance point X. And that each of these kernel can be assisted with some variance. Okay? And then another second approach to choosing the sets of this kernel function that is smaller to the training example. It says here, another second approach is that we need to choose this kernel function in such a way that it will be smaller than the sets of training example. And that turns out that when you have a set of training examples, say we have 10 instances, okay, it's better we choose the kernel function maybe to be 2 or 3, right? Because this approach can be more efficient than the first or the previous approach, okay? Especially when the number of training examples are large. So in summary, we now know that RBF function provides global approximation to a target function. Approximation provides global approximation to what? Target functions involving linear combinations, okay? Involving linear combinations. I'll just write here, linear combinations. And the second advantage is that what? That the network can be viewed as a smooth linear combination of many local approximations to target function. So which we can now put it this way, it provides efficient smoothing function or combination for many local approximation function. So in handling linear approximation functions, right? And finally, that this RBF method, okay, this RBF method can be trained to be more efficient than feed-forward network involving what? Back propagation. So we say it is better than feed-forward networks. Feed-forward network trained using what? Trained using backprop. So I will summarize the class now. So how did we start? We started by, first of all, looking at what? RBF, right? What exactly is it? How is it similar to your what? Locally weighted regression and your what? K-nearest neighbor? And what is the similarity between that and what? Your neural network. And these are the motivation behind that is that if we really want to get to convergence faster without actually wasting time on backpropagation, that we can actually train our model, our network, using what? RBF. And we took an illustrative example to understand how this is actually similar or different from your what? Network that is, how is it actually dissimilar or same from your what? Neural network. And then we summarize by looking at the key advantages. So in the next class, we will continue with what? Case-based reasoning.